So let's see how your classmates are doing. So far, still 12 people haven't submitted yet, but let's see the distribution. Okay, majority of you get most correct, and there's some below, but I think overall it's doing pretty well. So let's go over that briefly on the question. Okay, so let's get started. So the first question is rather simple, right? You can see the question is saying that the question is we have so sorry, I have to show the. Can you see the screen? Yeah. So what we have is X is uniform 10,000 to 30,000. Okay. And asking what is expected X, right? And we know the answer will be just average of these two numbers, right? Just 10,000 plus 30,000 divided by 2, so it's 20,000. Okay, because uniform, right? So it's just basically any number between these two numbers are equally likely. So the mean will be just the middle point, the midpoint. Okay, just nothing but just a simple application of that. Second question is very similar, but instead asking for the mean, is asking for the variance. Okay, so it's a uniform between 15 and 35. Okay, so the question asking what is variance of X, right? We know if X is uniform A and B, then the variance B minus A square over 12. So that means we have 35 minus 15 square over 12, right? That's 20 square over 12, right? It's 412. It's 100. 100 over 12 is 33.33. So the answer is D. Okay. I hope that's okay for this question. And yeah, no problem, right? So let's see another next question, which is slightly more challenging, I would say. So what we have a uniform between, X random variable for uniform 4 up to 10. Okay, asking the probability X is bigger than 8, right? Which is 1 minus probability X less than or equal to A, which is 1 minus F of A. Okay, and for uniform, right, you know that if uniform A to B, F of X will be B minus X, B minus A. Okay, so that's why it's 10 minus 8, 10 minus, typo. Is x minus a. So it will be 8 minus 4, 10 minus 4, okay? So it's 1 minus 4 over 6, which is 1/3, okay? Alternatively, if you remember, the probability is just the area under the curve, okay? So it's between 4 and 10, okay? And the height of this is 1/6, right? And the question asked is what is 8 and onward? So basically it's this area, okay? The base is 2, right? The height is 1/6, 2 times 1/6, which is 1/3 again, okay? So if you know this diagram, then it can be much faster. Or you can remember the formula, also can do. Is that okay for this question? So the area under the density curve, right, is probability, right? That's the meaning. Okay. So this, let me change the color. Okay. The red one is X. This is F, right? And uniformly from 4 to 10, right? And the base is 6, okay? So the height of this line is 1/6 because the whole area must be 1 because the probability must be up to 1 between any value between 4 and 10, right? And we're asking higher than 8, right? That means it's the blue area, right? Because from 8 to 10, right? They're asking. And this area, the width is 2, the height is 1/6, right? 2 times 1/6 is 1/3. Is that okay, Troy? Yes, but okay. What's the question? You can unmute if you want. Oh, the reason is this is the probability, right? Of the sample space. The probability of sample space must be 1. So this the height is the probability function. So let me forget. So let me get back to the let me get back to the slides. So wait a second. So I can show you the slides. That's what we have there. What do you mean by accessible? So here, not probability. Is the random variable. So can you see the slide? And the uniform here. Oh, just the attendance for the quiz. So the height is given by that. Okay, so I hope it's okay by now. Then the next question would be where disease follow the mean 10, right? So basically it's x is following exponential with lambda equal to 10. No, lambda equal to 1 over 10. Why? Because expected x is 1 over lambda, okay? That means 10 equal to 1 over lambda. So lambda is 1 over 10. And the variance of x is 1 over lambda square, okay? So it means 1 over 10 square, which is 100. So that's why we have C. Is that okay for this question? Oh, someone asked me why there's no 2. And no, there's no 2. If you probably you didn't aware, I think I correct the mistake in the slide, there's no 2. If you didn't notice, check back the video we have, there's no 2. And also in the proof, we don't have 2. So just make sure, yeah, it's a good way to see whether you follow what we have. And anyway, so this is almost the same question, but asking the other way around. So x is exponential with lambda equal to 1 over 10. Okay, same idea we have seen the last question, and asking probably x as less than 5. Okay, and we know exponential is e to the lambda negative lambda x, right? And in this case, is e to the 5 over 10. Okay, so that is the answer D. Is that okay? Just simple plug in. I hope there's no problem. Then we are going to the next question. So question 6, okay, question 6. This is asking the following. If the value of cumulative standard deviation and z is this, right? So basically fz is 0.8770, okay? Or 1 minus probability, or probability that z is less than z is 0.8770. What is z, right? And to do this, right, you remember the formula we learned is norm standard this, okay? There are 4 numbers here. You put in each one of them, then you know the answer, right? Let us do it in Excel, okay? So let me share the screen. Can you see the screen? Can you see the Excel spreadsheet? Yes. So we just input the 4 number, right? The easiest way is to use the Excel function to, okay, and then we will do the norm this, right? This value, and then true, right? And then just scroll down or double click this one, right? So this one is the answer we want. All right, so let me show you the formula test again. Okay, is it okay? Is it okay? So the other way around is now we have multiple choice, right? So we know how to do it, right? Is there any way the Excel can solve the problem reversely? Okay. So is it okay to have, I have 8.77, I can get this 1.16, okay? The problem's like this. The answer is yes. We have a function called norm standard inward, okay? You just input this number, okay? So give us the answer. So it will be norm standard inward, okay? So this is something that you reverse the outcome. You find the number that lead to the probability. Okay, is the inverse of the probability function, cumulative probability function, inverse of CDF. Is that okay? Good? Is it good? So now go back to the question again. I hope you can see it. So the next question is very similar and trying to do it like another number, okay, 0.209, right? And let's do it in the Excel, all right? We will do the norm reverse, right? 0.2090, right? And just double click this one, right? It's negative 0.80, okay? And see the answer is A, okay? So now we go to the next part is we go to question 8, okay? Question 8 is rather simple question of normal distribution. X is normal with mean 50, right? And standard deviation 2, so it's 2 squared, right? Where sigma is 2, okay? And sigma squared is 4, okay? And asking the probability that X is between 47 and 54, right? Then what you do is convert it into Z, right? By subtracting everything from the mean as a first step, okay? And divide by the standard deviation, okay? Negative 3 minus 2, negative 1.5, Z, and 2, okay? So this is f of 2 minus f of negative 1.5, okay? So let's see this thing in Excel. Okay, we need, we're asking X, Z is between negative 1.5 and Z and then 2, okay? Change the text. Okay, so that is norm as this 2 true minus norm as this negative 1.5 true. Okay, so it's f of 2 minus f of negative 1.5. Okay, so this is one way to do it, right? But we can do it by looking at the normal disk directly, right? So we can, because we want 47 x 54, okay? And we know the mean is 50 and standard deviation is 2. Okay, so we can just use the norm this. Okay, 54, mean is 40, standard deviation 2, true, minus norm this 45, mean is 50. Sorry, this mean is 50. Standard deviation is 2, true. Okay. So regardless of what you want, sorry, it should be 47. Okay, so you can see the same result there. Is that okay for this one? Okay. So the very last question. So we have the x, okay, has normal with mean 3.2, okay, and variance 0.8, okay. The question is asking x is less than 2.2, okay. Either you can use the same way we do, or use the quicker way to do it, okay. Or you can convert it z is less than 1.25, okay. Regardless of the way you do, that will be the same. Okay, why 1.25? Because this is 2.2 minus 3.2 over 0.8. Okay, so maybe I can show you in Excel. Okay, this is z is less than negative 1.25. Okay, this is x less than 2.2. Okay, and we have norm SD negative 1.25, true. Okay, and or alternatively we have norm dist 2.2, mean is 3.2, standard is 0.8, and true. Okay, so regardless of the way, that is the answer. So the answer is A, is closest to 0.1. Okay, any question? Any question about the? If no, then we just have a break, because now it's already. So let's just a break until 3:30. So let us review what we have covered last time, and then we can talk a little bit more. So just a reminder that you will be submitting your homework tomorrow. Okay, that deadline is tomorrow. Okay, so someone submitted to me directly, so please don't do it. Okay, because someone sent it to me, just please submit to the Blackboard. And it will The homework 2 will be released. You have 2 weeks to do it. So it will be questions on chapter 3, 4, and 5 in the textbook. Okay. So you will see it soon. So let's work on the sampling distribution. I guess we will finish all of it, or if not, then just left 1 or 2 pages. So just to review a little bit, the simple random sample. Can you see my slide? Yeah. So which means each have equal likelihood being selected. Okay. And which means that each observation have the same distribution as the population, and they're the same mean and same variance. What it means is if x1 up to xn observation or simple random sample, and the population have mean mu and sigma square, expected value xi is mu, variance xi is sigma square, and any unrelated observation have covariance 0. Okay, so I just write down it explicitly. Okay, but it's already in your a version of the slide, but it's just more explicit. The sample mean, last time we covered, is the mean of the sample, right? Just adding all the observation over the number of the sample size will be the sample mean. And because each observation is a random variable by itself, some of the random variable, right, is still a random variable. Okay, so x bar is also a random variable. Depends on what you have. Okay. And one interesting fact will be, which we will show, is the expectation, because this sample mean is a random variable, right? So we can tell expectation, and turn out to be the expectation is the population mean. Okay. In the other word, in terms of understanding, is if we do a lot of samples, right? Of course, in the real world, we just do once, but in theory, we can do many samples, and each sample will give you sample mean. And the mean of all the sample mean, right, which is expectation, is the population mean. Okay, so that's what it means. And this nice property is called the unbiasedness of the sample mean. Okay, so to illustrate the significance of this result, and let's see the following example. Okay, different example. So the population of 3 numbers, 1, 2, and 3, right? And of course, each of them equally likely. Okay, and that means that we have probability of, because it's simple random sample, right? So which means that probability of 1 equal to probability of 2 equal probability of 3 is 1/3 if you run a simple random sample. Okay, and this, the sample mean is adding, the population mean is adding the 3 number up divided by 3, which is 2. Okay, now if we have sample size of size 1, okay, size 1 instead of 2, then we only have 1x, right? x1, right, is equal to 1, 2, or 3, right, with probability 1/3, 1/3, 1/3, right? That is what it means by simple random sample, right? And the mean of the sample mean, right, is also the same thing, right? Because the only one observation, what it draw is the sample mean by itself, right? So that exactly saying the sample mean is the population mean. Okay, mean of the sample means population mean. And now we try the sample of size 2. Okay, simple random sample means that the sample mean will be one of the following 9 possibility. okay? Because each sample you draw is equally likely, right, up here. So 1/3 you have 1, 1/3 you have 2, 1/3 3 for the first draw, okay? For the second draw, you also 1/3 is 1, 1/3 is 2, and 1/3 is 3, okay? If the first draw is 1, second draw is 1, okay? The mean, the sample mean is 1, right? Because 1 plus 1/2 is 1, okay? If first draw is 1, second draw is 2, then it's 1.5. So and so forth, you can complete this table, right? Because this is, we want the sample mean, okay? And these 9 cases are equally likely, okay? So the 9 possible sample mean, right? And they're equally likely. So the expectation will be 1 times 1/9, and 2 times 1.5, right? 3 times 2, 2.5 times 2, and 3, okay? And then you can easily see that we add up, we get you 2. Okay, so that is the, because this is 5, okay? This is 6, and this is 3, this is 1, right? And this is 10, this is 15, and 3, right? It's 18/9, so it's 2, okay? Which part you don't get it? The whole thing? Someone asked me to sample size 2, okay? So we are doing simple random sample, right? So the first case you can have 1, 2, 3, right? And for each 1, 2, 3, you also have 1, 2, 3, right? Because we do simple random sample. So that's 9 possibility, right? When you have 1, 1, the sample mean is 1. When it's 1, 2, the sample means 1.5. When it's 1, 3, the sample means 2, okay? So this is table. Do you get that? Okay? And this all 9 possible sample mean. So what is the mean of all these sample mean? Okay? And the appearance of this is equally likely, right? So that's why the sample mean, right? Actually, the random variable is 1 with probably 1/9, okay? 1.5 with probably 2/9, 2 with probably 3/9, okay? 2.5 with probably 2/9, and the last is 3, probability 1/9, okay? Then the mean of this is 1 times 1/9, 1.5 times 2/9, and 2 times 3/9, and 2.5 times 2/9, and 3 times 1/9. Then that gives you 2. Is that clear? Good. So that is why we mean mean of sample mean. Okay. Thanks for asking. And now this is the case of sample size 2, right? Well, sample size 3, you need to do the same again, right? But we can easily show it in the math, okay? There's no need to do this in this way because it's much easier, okay? So we rely on the old thing, expected AX is A times expected X. Sum of the expectation of the sum would be equal to sum of the own expectation. Okay, we'll use this to fact. Okay, so expected value of the sample mean, okay, is by definition is mean of expected value of sample mean, right? This notation. And for this, we write the meaning of the sample mean, right? Is sum of all observation over n, okay? And we invoke this to here, take the 1/n out, okay? What you left is summation. And summing, right? You can put the expectation side in, this is what it means, right? So that's why it's this. And each observation is mu because it's a simple random sample, right? So the n of them, those are the n mu. And n cancel out, that left mu. Is that okay? So here is the steps here. And a question about this, okay? Of course, you can remember this, but this is the proof. Okay, you can remember this fact, but this is what the proof is. Is that okay? Any question? If okay, can I have you say okay? Good. Then we will go to the next step, okay? We know the mean of the sample mean is the population mean. But what about the variance of sample mean, okay? Do we know anything about that, okay? Turn out to be, which we'll prove later, okay? Turn out to be the variance of the sample mean, okay? Or what is this one is sigma square over n, okay? So it's reduced by sample size, okay? You can easily see from this expression, when n go to infinity, this sigma will go to 0. The reason is rather simple. You can imagine this, okay? Consider any distribution, okay? Because we don't require to be normal, okay? Now, consider that you now do the sampling and you do many sample, as what we said, do many, right? So we just get a lot of sample, many of them, just random sample, right? Just get, right? And we get all this value, right? And if you get n to infinity, right, get many sample, right? So the mean of the sample mean, right, will be very close to population mean, right? Because you get almost every time all of them, right? Then it's very close to the distribution by itself, right? And every sample you get is close to the population mean. That means that there's no variability, there's no variance. That's why it's 0. Okay, that's the intuition, right? Because just like you consider urn of many balls, and you get every time you just get a ball and put it back, get a ball, put it back, get a ball, put it back, right? Then the sample outcome should be very close to what actually is inside, right? So that's why there's no variation, okay? And some notation, term standard error of the mean, right? It means that the square root of this. So that's why take a square root. Okay, so this that's definition. Okay, so there's nothing to understand, but just you know it. Okay. Okay, so now I'll give you example to see if you get this idea. Okay. So again, the same question. We have 3 numbers. Okay. The sample mean. Sorry, the population mean is 2, 3 are number, each term equally likely, right? And the population variance will be each number minus the mean square, right? 2 minus 2 square, 3 minus 2 square, right? This is 1 plus 0 plus 1 divided by 3 is 2/3, okay? So the sigma square is 2/3, okay? Mu is 2 here. Now consider the sample of size 2, okay? Same as before, the first number you drawn will be 1/3 likely for each, right? And the second draw is also 1/3 each. The reason is because each observation will be equally likely, right? And they're independent, right? The first draw is independent of second draw, okay? So that's what we mean by simple random sample, okay? And this is the sample mean, right? This 1 plus 1 over 2, right? 1 plus 2 over 2, okay? This is how you get this table. And result in the previous example is 2, okay? Now, we want to know the sample mean, okay? How you get it, right, is each observation is 1/9, so it's 1/9. 2 minus, sorry, it should be 1 minus 2, okay? 1 minus 2 square, okay? And this also 1/2, 1/2, sorry, 3/2 square, okay? So that's why you have this 1 square times 2, okay? And then you notice that different from 2 is 0.5. Actually, there are 4 of them. This, and this, okay? So that's why it's 4/9, 0.5 square, okay? And then 2, okay? It's the same, so you don't need to calculate. So add them all up, okay? This is 2 plus 1/9. This is 1, okay? This is 3/9, which is 1/3, okay? But you can rewrite it as 2/3/2. Why? Because this is sigma square over n. Okay, so that shows you why the variance, the sample mean, is sigma square over n. Of course, this is an illustration. We'll do the proof immediately. But did you get the idea what we are doing? Okay, since I didn't see any question, so let's go ahead. Okay, so we use this formula which we know already. Variance of AX, we take A squared. The variance of two number, okay, where the sum will be sum of their variance if they are independent, okay. We'll use this fact, okay. Sigma square of the sample mean will be just by definition is variance of this sample mean. And sample mean is sum of all observation over n, okay. Now we invoke this first property, okay. To the n out, 1/n out, so that's why 1/n squared, okay. And now we invoke the second one, variance of the sum is sum of the variance if they're independent, because they're sample simple random sample, you can take the variance in, okay. So that's why variance. And each variance is sigma square, okay. N of them, so that's n sigma square, and n cancel out, so that's why you have sigma square over n, okay. So that's a proof. Is that okay? Any question before we proceed? Because we will talk about the single most important result in this course, I would say. Are you ready? There's no question. No question? Good. So we are going to talk about this single most important result, okay? So what it means is the sample mean, right, of a simple random sample has a normal distribution, okay? When you have large enough sample, okay? Even though whatever you draw, okay? What it means is, the interesting part is, no matter what the population is, okay? This is population, okay? The sample mean, okay, is always a bell shape. If this have the mean mu, variance sigma square, this sample mean is always mean mu, okay, with sigma square, which we know it. This is something we know already. We just proved this, okay. The importance of central limit theorem is it is a bell shape, okay. It's a bell for a bell curve. The bell curve is the key of this theorem, is a bell curve, okay. It's regardless of what it is, we don't need to care about that. When you have a large enough sample, the sample mean always follow this bell curve, okay. So that's why this is very important, right? Because what we get in the data is sample mean, right? Knowing if the bell curve will help us to do what we need to do in the next week, okay? The estimation and all this thing. Okay, so so this is already known, right? Because this is expected X bar, and this is variance X bar. The important point again, the repeat is this normal, okay? And if we write, right, it means that this X bar minus standard deviation, right, is equal to normal CO1. Is that okay? Because this is the single most important thing and we're using it for the rest of this class. Any question? If okay, then can you type okay? Because it's very important. I'd like to have a confirm from you. Okay, thank you very much. In case you don't know, I can just go over again, but since everyone say okay, so let's continue, okay? Let's have example, okay? Consider population, okay? Has mean mu equal to 5, sigma square is 64, so it means sigma is 8, okay? And sample size 100, so n is 100, okay? So the question is, the sample mean is no more than 4, okay? So the sample mean is no more than 4, right? And because, right, X bar minus 5 over 8 over root 100 has a normal CO1. This is central limit theorem, okay? So you need to subtract both side by 5, divide both side by 8 over root 100, right? So that's why you have this. And this is z, okay? And this is negative 1 over 8 over 10, right? So it's negative 1.25. And so do note that there's typo in your version, so there's extra 0 there, okay? Just make sure that when you check it, you know it. So then you would do the normal, okay, standard this. I think after the quiz, you know why we need that, okay? How we do that. So this gives you this number. Okay, any question? Any question? No? Okay. Is there any question on this one? If no, then we'll go to the next one. So let's talk about some special case, okay? In just special cases to basically we are restating our result. So the question is why, oh, okay. So first question is why 8 over, because okay, this is sigma over root n, okay? Sigma square is 84, sigma is 8, n is 100. Is that okay, Choi Lam? And for other question is how big the n is. For application purpose, n bigger than 35 or 30, you might use you may use it. Okay, so that is the rule of thumb. Sometimes you need more, of course, more the better, but at least I would say if less than 30, then you would not use it. Okay, but of course, for most practical purpose, then you would see that you would need quite a few number of them. But n2, no, it's unrelated to n, yn. There's no n here. Because, okay, you're confused with the idea. The variance is sigma squared over n, okay? It's given the n, then we can do this infer. So, Vicky, do you get what I'm saying? The normal invert, okay? The norm is not for this purpose. This is the purpose trying to ask this question. Asking, say, what is this value equal to, say, 0.5? Okay, actually, no, it's 0, but you want to know this, what is this number? Okay, give you the probability. You go to invert, then you put 0.5, this will give you 0. Okay, because this is, 0, symmetric, right? So this is 0.5. So just give you the probability you want to find this number. So this is what the norms as inward means. Okay, Vicky? So the next part will be just asking is either 0 or 1, okay? And in this particular case, if the x0 either 0 or 1 just like a categorical variable, either say sometimes it's like whether someone have done something, where maybe say, have you ever tried this product, or X is whether probability success, or it's binomial trial, right? Or binomial trial in this case, right? Because each random variable, then the sample mean, right, will be pi, okay? And the variance will be pi times 1 minus pi, because this is a binomial trial, okay? So we don't need to have mu and sigma square, right? Because for if the population, right, x, right, is only either 0 or 1, okay? And in that case, this probability p and this probability 1 minus p, right? So the x is p, right? And the variance of x is p times 1 minus p, right? This is coming from the binomial distribution, okay? And in this case, we will use the pi to denote the population, okay? The sum average, okay? We call proportion, because the average of them turn out to be is the percentage of them, okay? So the sample proportion, okay, is the sum of the x, which is either 0 or 1 over n, right? Is the proportion of them, right? Because 1 is they have, 0 they don't. So average of them is either 1 or 0 over n is the proportion, okay? So we denote as p, okay? Just simple sample mean, but we call it the sample proportion p, okay? So there's no different from what we have before, but we just, the value is either 0 or 1, okay? That is the only thing that to be concerned here, okay? And in this particular case, okay, what we mean by sample proportion will be, you can simplify further by pi times 1 minus pi over n, and the standard error proportion will be pi times 1 pi, okay? Just in this case, and then the central limit theorem for proportion, right, will be the same, okay? Pi times 1 minus pi over n, okay? Pi. And in this case, just to remind you that if the n should be n pi times n times 1 minus pi, if they're at least 5, okay, bigger than 5, then central minimum theorem is a good approximation. Okay. Okay. And the next is, I think you should jump one more slide because I swapped the order. Okay. So the same idea here, we have the sample population is 0.6, okay? And sample size is 100, okay? And what is the sample proportion that is less than 0.55, okay? So n pi is 60 and n times 1 pi is 40. So they are more than 5. So the central limit theorem would apply, okay? And P sample mean is less than this number will be equal to this minus the n pi, right? And then will be over n pi times 1 minus pi over n, okay? So this is here, okay? So basically this comes from central limit theorem, okay? And this number turned out to be negative 1.2, and that's why you have this result. Is that okay? Okay, so basically there's nothing but just applying that formula directly. Okay, there's nothing new. Okay, you can see I skipped one slide because I think that's technical. Okay, so I just I figure out that I just create technical. So what it is I rewrite a little bit. So basically what it said is if x is binomial with n and p, okay, and if n p bigger than 5, n times 1 minus bigger than 5, then this can be written as normal np np1 minus p, okay? So that is what I want to say, because I think the original, the one uploaded is a little bit tricky, okay? It's not easy to understand, I rewrite a bit. So what it means is the binomial, okay, sometimes complicated, but you can, using the normal to do approximation, okay? And this is called the normal approximation of binomial, okay? But I think this is too technical for our purpose, so I just put it technical, okay? So feel free to, don't feel bad if you don't follow, because this is not, I just cut it out from our syllabus, okay? Because I don't think that is super important. And the proof is actually rather simple, okay? We have just this thing, if x are either 0 or 1, it's binomial, right? And np or np bigger than 5, okay? Central limit theorem apply. The sample proportion follow this this is central limit theorem, okay? And if you multiply n, right? So the mean will multiply n, and the variance will be multiplied by n squared. Okay, so that's why cancel out, become np times 1 minus p. And this guy is because sum of the binomial is binomial, okay? So that's why they are the same, okay? That's what I said, okay? Binomial can be approximated by a normal when NP and N minus P are at least 5, okay? So that is what it means, okay? Is that okay? But I decided that this part should be in the technical rather than in the in your text. Is that okay? Any question? No? If that is the case, so now we are going to give you the very last result, okay? This is just a very simple minor changes to central limit theorem, okay? Central limit theorem said, right? If we have a simple random sample, okay? The sample mean minus the population mean over the standard error, right? Is sigma over root n is standard normal, okay? But the question is, okay, we may have sometimes have good knowledge about the sample mean, right? Because from history of data, we may have done some similar sample. The sample mean is easy to estimate, right? But how for the population variance, sometimes it's very hard, okay? We don't even have any idea, okay? And very naturally, we often want to use the sample variance to replace the population variance, okay? So the question would be, oh, instead of having this, right, what about this guy, okay? Do we know about this? So if you ask what happened, okay, if you ask what happened instead of the sigma, right, because we don't know sigma, okay? So this is the main question here, okay? Now, the answer is rather simple, okay? Is student, okay? Pen name of a statistician, Gozet, in 120 years ago. What he's shown is if you replace it by the sample variance, right, which is defined as x minus x bar over n minus 1, okay? This will follow a distribution called student t, okay, with the real term n minus 1, okay? You have n sample, it becomes n minus 1. Is that okay for this one? Okay, so this is very, very important, okay? So the central limit theorem said x bar minus mu over sigma over root n is normal, 0, 1, or cos z, right? This is central limit theorem, okay? And a related result will be if we replace sigma by s, we have t n minus 1. So this is very important result. So we'll not prove it. We may talk about the proof next class, but we talk about its application. Okay? So there's nothing to understand because this is the result given to you. So this is the result. Just let you know this is the result. Now, let us look at the example. Okay? So population with mean 5. So can be anything. I don't know what it looks like, but I know the mean is 5. Okay? So we don't know the sigma square. We have no idea. Okay? And how we get 5, maybe from historical data, some other knowledge, tell us it's 5. Okay? We believe it is true. And now we're going to have a sample of 100. So we just draw 100 sample of it, and it's 100. Okay? And the sample variance, right, is S squared is 8. Okay? So the question is, what is the sample mean, okay, is less than no more than 4.5, okay? Or should be equal to, but doesn't really matter, okay? So from what we have just now, the student, okay, have shown this, okay? X bar minus 5, okay, sample mean, over S, which is 8, okay, over root 100, have a t distribution with 99-degree of freedom. Okay, so this is proven by the result that we haven't proved it, but we'll talk about some outright proof for you next class, which the last 2 slides. Okay, that means that asking this question is equivalent to subtract 5. Okay, do note that your slide have forget 0.5. Okay, and divided by it's x squared, because s is square root of 8. So it should be square root of 8. Okay. And okay, so this is the result is negative 0.5 over root 8 over 100. Okay. This t, how do we solve this problem? We will use Excel. Okay, so let's go to the Excel. We will be negative 0.5 over square root 8 over 100. Okay, so let's see the Excel. Okay, now what we want is negative 0.5 over square root of 8 over 100. Okay, so this is a quantity. Okay, what we want is we want the t distribution. Okay, will be t distribution. Okay, and then you put this number. Okay, you want to find, and different from the z, right? The t will give you unit degree of freedom, which is 99 here. Okay, because 100 minus 1, and it's true. Okay, so this is the answer. Okay, so that's why it's 0.0 is like 4%. Okay. Okay, so this is 4%. Okay, so if you use the wrong z, okay, it will be very close. Okay, because when the sample size getting larger and larger, actually there's not much difference between t and z. Okay, so let's see from the Excel, if you do z, there will be not too much different. Okay, so let's see z. Sorry, it's normal. Okay, standard this. Okay, and this number true. Okay, is very close. Okay, I think I should stop here. I think it's almost time. So remember to submit your homework tomorrow. The new assignment will be released tomorrow. Thank you. Bye-bye. Have a nice weekend. Just remember to submit your homework. I'll stay around to answer any question you might have. You don't have to do the very guide yet. No, for this, no, you don't need to. Yeah. There are some function in Excel with a dot. The dot one is the new one. Okay, without dot, there's a classical one. The difference is that there's some efficiency improvement and some correctness. Is new version. Is that okay, Chuckman? That is just the old version Excel don't have dot. New version of Excel you have no dot. So new version have dot. The old version have no dot. That's the only difference. And of course, there's some updating the thing, but just the dot one will be the one that you should use because you're using new Excel, right? Unless you go back to the old days, the old Excel machine, they don't have that. Same for this, I think Excel, Google Spreadsheet are the same issue too. Okay, let's see if anyone have any further question. Any more question? If no, then we will end the section and you guys have a very nice weekend.